Now in this lecture, we shall be discussing about calculation of, we can say, CPE factor also and CPI also. And in addition to that, as you know, in the earlier lecture, we have discussed in detail about the CPE calculation. And there are these other factors also. One factor that we have not yet discussed is the action combination factor, that is KC. So KC, that is visible from here. Here we can see that how this KCE is written, and for the internal pressure, it is KCI, that is action combination factor for internal pressure. So these, except for these factors, which we shall be discussing in somewhat brief in this lecture and in somewhat detail in the next lecture. But for clarity, I just want to explain you how you can calculate the CPE for the actual structure, so that the concept is clear to you that how these things needs to be done. I don't want to be this class to be purely theoretical, because otherwise I would have simply explained the KCI first. I want this class to be practical. So let me just explain you all the concepts here. So first of all, if we are talking about the wind pressure coefficient, now in this lecture we shall be discussing about the external pressure also and internal pressure also. So if we are talking about the, we can say, external and internal pressure. So if you're talking about the external pressure, CSHP, so that is basically CPE, that is the one that we shall be finding out from the tables on the right hand side. Ka is the area combination factor. So if we're talking about the Ka, that is, we can say, area combination factor, that is basically given in clause 5.4.2. So if we want to find out the value of the Ka, that can be calculated from 5.4.2. And the basic concept is that the larger the tributary area, the tributary area means that the area on which the wind shall strike and effectively put pressure on the building. The larger the tributary area, the lesser shall be the value of the Ka. So if the tributary area is very less, that is let us say less than 10 meters square, so for that the value of the area reduction factor Ka shall be 1. But if the tributary area is very high, let me just show you the table also. Yeah, this is the table. So if the tributary area is high, so in this case we can see here that it is 100 meters square. So for that the Ka value, that is area reduction factor Ka, comes out to be 0.8. The basic concept is that the larger the surface area or the tributary area, let us say if we are talking about the area which is 200 meters by 5 meters, so we cannot say that the wind shall be striking at the same intensity across the full length and across the full width. There shall be a little bit of higher on one side and there shall be a little bit of lower on the other side, or on the other, we can say the area. So that is why the averaging is done, and as per the wind tunnel studies, or as per the actual theoretical studies that had been done, these values have been calculated, and the in simple word, larger the tributary area, the lesser shall be the value of the area reduction factor, that is Ka. Now coming back to the lecture, we very well know that we are right now talking about the following calculations. Basically calculate the external and internal pressure coefficients for an enclosed rectangular building. Now the coefficients have been combined with wind pressure for each orthogonal direction. The combination of external and internal pressure needs to be conducted separately. When combining the pressures, the combination factor KCE and KCI, now these are given in the table 5.5, which we have not discussed yet. But just to give you a, we can say, brief preview, I had already discussed in the earlier lecture also. Now when we are talking about the wind pressure calculation on whole, on the complete structure, let me just show one figure here. Now let us say we are talking about the wind pressure calculation on this kind of structure. Now there may be a case where only effectively, we can say, wind is striking on this particular wall only. The wind is not putting any much of impact on the external, or we can say the wind is putting only external pressure impact. So effectively we can say that, let us say the wind is acting on first surface, that is outer surface, the second, that is outer surface, and the third, that is outer surface. So in that, basically what happens is that the number of effective surfaces determines the value of the Kc, that is the combination factor. So when there is this combination of the, we can say, windward wall, roof side wall, leeward wall, or we can say internal walls. So all of these, when they're acting together, or there is this combined action, so the more the number of, we can say, surfaces, the more the number of effective surfaces, the lesser shall be the value of the KCE and KCI. Now the minimum value of KCE is 0.8, and the maximum value of the KCE, that is 1, and the same is valid for the KCI also. So there shall be, we can say, combination factor for the external pressure coefficient and combination factor for the internal pressure coefficient. So KCE and KCI, when both of them, we do need to find out when we are, talking about the actual practical structures. So that was the introduction to KCE and KCI. Ka is also clear to us, and KL is the local net pressure factor, and P is the porosity factor. And when we're talking about the internal pressure, so for internal pressure, we have to find out the CPI multiplied with the action combination factor for internal pressure and multiplied with the KV. That is the volume, we can say, open area divided by volume factor. So that we had already discussed in the section 5. So that is given in the section 5.3.4 of the code. Now, when we are talking about the building, let us say the building that we are right now talking about, the height, average roof height of the structure. Let us say the average roof height is 10 meters. Now in here, this is the average roof height, and that we have assumed it as 10 meters. After that, the dimension AA. This is the dimension A. In the language of the code, we can say this is basically B, and the BB dimension, this is basically D. So now when we are talking about the A, this is basically, I'm again writing it here, that this is basically B and this is basically D. So alpha, the pitch of the slope, that we have assumed it as 10 degrees. Now ratio for theta is equal to, we can say, 0 and 180. It means that when we're talking about the wind incident angle or the direction of wind at, we can say, 0 degree and 180 degree. So for that, the value of D, or we can say, that in that case, basically the B shall be AA. So that is why, for this particular figure, we do need to find out the value of D by B. So when we are going to, find out the value of D by B, so D in our case is basically, we can say, BB. So that is 30. So 30 needs to be divided by, we can say, 75. So that value, that is D by B, comes out to be 0.4. And H by D is basically, we can say, H is the average roof height, that is 10 divided by D. That is, in our case, D is basically BB. So in that case, 10 divided by 30, the value comes out to be 0.33. So that is clear to us. And after that, when we're talking about the ratio for theta equal to 90 or 270, in that case, the direction of B and D becomes opposite. So this, when we're talking about the theta is equal to, we can say, the 90 or 270, in that case, the value of, we can say, A divided by BB. So it becomes opposite. So we can say that 75 needs to be divided by 30 here. So the value comes out to be 2.5, and H by D, that is 10, that needs to be divided by, we can say, 75. The value comes out to be 0.13. So that is the basic calculation when we want to find out the ratios here. So D by B for theta equal to 0 is 0.4. H by D for theta is equal to 0, 180 is 0.33. D by B ratio for theta equal to 90 degree or 270 degree, that is basically 2.5. And H by D ratio for theta is equal to 90, that becomes 0.13. So when, this is the practical picture here. So in here, when we are talking about the enclosed rectangular buildings, we are talking about the gable roof with ridge. So this is basically the gable roof, and this is the ridge. And gable facing, we have assumed it as basically 90 by 270. So for the first case, when we are talking about the, we can say, calculation of the these coefficients. So the first table that we are right now discussing is that coefficient for gable roof with ridge when alpha is greater than or equal to 10 degree and gable is facing orthogonal 90 and 270. So this is the picture. We can say that this is how it shall look when we're talking about the calculation of coefficients. Now the second thing is that the direction, this shall be 0, this shall be 180, this shall be 90, and this shall be 270. This is clear. H by B, D by B ratio for 0, 180, 90, 270, that is also clear. Alpha shall be same in both the cases. Alpha for theta equal to 0 shall also be 10 degree. Alpha for theta equal to 90 or 270, that shall also be 10 degree. Now, the second thing that we do need to understand here is that we do need to refer to table 5.3a. So in table 5.3a, basically we are talking about the roofing arrangement first in the first trial. So for the roofing arrangement, we can say that for CPE for alpha equal to 10 degree, and when we're talking about 0 to 0.5 h here is basically 10 meters. So we are talking about 0 to, we can say, 5 meters, and in here we are talking about theta equal to 90. So we can simply refer to this particular table here, and in here, table 5.3a. So you need to understand here that, when we are talking about the wind striking from this particular direction, that is either from theta is equal to 90, or we can say from theta is equal to 270 degree. So when wind is striking from, we can say, this particular direction, so in that case, the roof encounter, that shall be a kind of, we can say, monoslope roof. So for monoslope roof, we very well know that we have to, refer to, we can say, table 5.3a. So in the table 5.3a, basically it is given that for monoslope roof R, we have to, refer to this particular values. So for 0 to 0.5 h, let me just zoom in here. So for 0 to 0.5 h, we can refer to the value h by d. Now h by d ratio that we have calculated in our case for theta 90 and 270. So for theta 90 to h by d ratio is basically 0.13. So that is less than or equal to less than or equal to 0.5. So that is why, we do need to refer to this particular values, that is minus 0.9 and minus 0.4, which have been considered here. And after that, the from 1h to 2h, the values are minus 0.5 and 0, the one that has been, considered here. And after that, when we're talking about 2h to 3h, the values are minus 0.3 and 1. And for greater than 3h, the values are minus 0.2 and plus 0.2. So that is why, all of these values have been considered from, we can say, table 5.3a. As, when the wind is striking at theta equal to 90 and 270, it is not a, we can say, pitch roof. It is just a monoslope roof, because there is no as such, apex and the highest and lowest point. It is just the crosswind, phase that is being encountered. So that is why the table 5.3a is considered here, that is with we can say R, that is crosswind. And when we're talking about theta equal to 0, and we are talking about this theta equal to 180. Now when we're talking about theta equal to 0 and 180, we do need to refer to table 5.3b, because in that case, that is a table, that shall give us the correct values. So let me just show you the table 5.3b. So this is the table 5.3b, and for, we can say, upwind slope alpha greater than or equal to 10 degree. Now h by d ratio that needs to be determined. H by d ratio for theta equal to, we can say, 0 and 180, h by d is 0.33. So the values need to be interpolated, as the values are given for 0.25 and 0.5. So after interpolating values for alpha 10 degree, so the interpolation needs to be done between these four values here. So the value comes out to be minus 0.77 and minus 0.33, that is interpolated between minus 0.3 and 0.4, and interpolated between minus 0.7 and minus 0.9. So this is also clear. And after that, when we are talking about table 5.3 CD, so cross wind value is also calculated here, that is U value. After that, upwind value, that is also calculated. Now downwind value that needs to be calculated. So for downwind, basically we do need to refer table 5.3C, as we had discussed. So table 5.3C says that for, we can say, h by d value of 0.33 and alpha equal to 10 degree, So the values are basically these. We can say we need to determine between these two values. That is, h by d ratio is in between 0.25 and 0.5. So after interpolation for between minus 0.3 and 0.5, the value comes out to be minus 0.37. So this is how we can calculate the value of the CPE for theta equal to 0, 90, 180, and 270. Second case here is that when we want to find out the values for the walls. So if we are discussing about the walls, we do need to, instead of 5.3, we do need to go to 5.2. So for table 5.2a and table 5.2b. So it simply says that if our h is, we can say, less than or equal to 25 degree, and when wind speed varies with height h, that is this particular clause. So less than or equal to 25, and when wind speed varies with height, the values that needs to be considered is 0.8 for all the possible incident angles, that is 0, 90, 180, and 270. So in this case, all of these cases, we can simply find out the value as 0.8. After that, the second case here is that when we're talking about the levered wall. So for when we're talking about the levered wall, we are talking about table 5.2b. So when we are talking about the table 5.2b, we are talking about the options as roof pitch. So in our case, the roof pitch alpha, that is basically 10 degree. And for all values of d by b, the value is given as minus 0.3. So that is why for all the cases here, it is considered as minus 0.3. So we can say that for windward and leeward walls, the table is quite easy. We just need to, for windward wall, we just need to refer to table 5.2a. For leeward wall, we just need to refer to table 5.2b. And for side wall, as we had discussed earlier also, we do need to refer to table 5.2c. So for table 5.2c, the input values are not as such provided, that the ratio for, as per ratios, the values are being differentiated. These are the principally 4 values that simply we can take for CPE. So in here we can say that for all incident angles, that is 0, 90, 180, and 270, the values are given taken same, that is minus 0.65, this value. After that, for 1:2h, that is for distance of 1:2h along the side wall, it is minus 0.5. And for, we can say, 2:3h, the values are minus 0.3, the one that has been written here. And for distance greater than 3h, the values are minus 0.2, the values that has been written here. So this is how we can calculate the value of the CPE for 0, 90, 180, 270, considering different wind incident angles and considering the different h by d and b by d ratio. So in simple word, I'm repeating here, b is the dimension of the building perpendicular to the wind incident angle. D is the dimension of the building parallel to the wind incident angle. So if in this case the wind incident angle is theta equal to 180, this shall be the dimension of the B, and this shall be the dimension of the D. Second thing that we do need to understand here is that for different incident angle, we do need to do the grouping arrangement. Grouping is that 0 and 180 shall come together in one group, 270 and 90 that shall come together in the second group. According to that, we do need to find out the value of d by b. We do need to find out the value of h by d, and alpha, if required, that can also vary. So according to that, we can simply the important thing or the important concept is that when we're talking about the roofing arrangement and when we're talking about theta equal to 90, that is wind blowing perpendicular to the, we can say, pitch of the roof pitch, or we can say, sorry, parallel to the roof pitch. So in that particular case, the roofing considered shall be monoslope roofing considered. But if the wind is striking from theta equal to 180, in that case, obviously we have to consider the this gable roof with ridge arrangement. So according to that, we can simply find out the windward wall, leeward wall, side wall, external pressure coefficient. We can find out the, we can say, upwind, downwind, and crosswind roof slope coefficients also. So CPE values that we have right now calculated. After that, the second thing that we do need to find out are the internal pressure coefficients. So it we can assume that the internal pressure for table 5.1b, let me just show you the table. So assuming that the building in which we are right now calculating the load, the internal pressure coefficient, the opening that is greater than 0.5% of the area of the corresponding wall or roof. In that particular case, let us say this is the picture that is of the building. So in this case, let us assume that coefficient where ratio of opening on one surface to the sum of total open area is 1. So that we can simply refer to table 5.1b. So as per table 5.1b, we can see here that for ratios having value equal to 1. Now if the wind is striking from this particular direction, that is wind is striking from theta equal to 0. So in that case, largest opening is on the side wall. So for that, the CPI value, that needs to be considered as minus 0.3. So we do need to refer to these values. So in here we can see that the basically for the largest opening is on the side wall. That is when wind is striking on this particular direction, the largest opening is on the side wall. So in that case, the CPI value is minus 0.3. Now when wind is striking from this particular incident angle, that is theta equal to 90. In that case, if the largest opening is on the windward wall, so in that case the value that needs to be considered is minus 0.1, and CPI theta 2 as 90, that is plus 0.2. So both of these values, that is minus 0.1 and plus 0.2, that has been considered here. After that, when we're talking about CPI 2 theta equal to 0, so in here the second value was 0. So that is why the 0 value is also considered here. So that is the basic concept, and according to that we can simply find out the value of the CPI also. So I hope the calculation is now clear to you, that how you can find out the values of the CPE, how you can find out the values of the CPI. So according to that, we can simply enter all of these values here. That is, we can find out the value of the KA also, KCE also, KL also, KP also, KCI also, and KV also. And on the basis of that, we can simply find out the aerodynamic shape factor for external pressures and aerodynamic shape factors for the internal pressures. Now in the earlier lecture, we have already discussed in detail about how we can find out the site wind speed, design wind speed, and I won't be repeating that here, but the focus of this lecture was to explain you that how you can calculate the external pressures value CPE and internal pressure value CPI as per the AS1170 part 2. Now this might be a little bit confusing to you, so you can simply download this resources from the attachment, and you can study that again at your end also. And if required, you can repeat this lecture, because if you're reading this for the first time, it might be a little bit confusing to you. But trust me, with the practice, the things become much more simpler to understand.